In each of these examples, we're going to determine whether each model is linear or exponential and how we can tell. Then we're going to generate an equation to solve the problem. The first example says the value of a $20,000 car depreciates at a rate of 18% per year after it is purchased. What will be the value of the car after 5 years? So first we have to determine if it's linear or exponential. This is an exponential situation. And the reason you can automatically tell is because the car is depreciating by 18%. Depreciating basically means decreasing. We're decreasing by 18% every single year. Whenever you're increasing or decreasing by a percentage, that means there's a pattern of multiplication. Because think back to when we were working with percentages. For example, when we were adding on 7% tax or applying a 25% discount, every single time we performed those calculations, we had to use multiplication. So whenever you're manipulating numbers using percentages, you have to use multiplication. So that right there is a immediate indicator that this represents an exponential situation. Now that we know it's exponential, we can write an equation representing this situation. So the tricky part about writing exponential equations is that when you're increasing or decreasing the numbers by a percentage, this basic format does not really work, because technically 18% is not the decay factor. Let's say we try to write the equation using the basic format, using a times b to the power of x. So remember, a is the initial amount, right? Our initial amount is 20,000. Let's say that we assume 18% is the pattern. So let's say we just plug in 18. We assume that's the factor. That wouldn't really work because this number is greater than 1. So what's going to end up happening is all of your values are going to increase. Our value should not increase because the value of the car is depreciating. It's decreasing. For example, if you try to solve the problem by plugging in the number 5, so let's say we try to plug in the number 5, and since we're using exponents, let's pull up a calculator on Google. 20,000 times 18 to the power of 5. You get a really big number. This number is 37,791,360,000. That doesn't make any sense. Obviously, the value of our car is not going to be worth that amount of money after 5 years. So I know it's not 18 inside the parentheses. Let's say you tried plugging in 0.18. So let's say you assumed that was the equation and you calculated the value of the car after 5 years. What's wrong with that is you're going to end up with an unusually small number. This is $3.78. $3.78. The value of the car can't possibly be that small. Given that the percentage is not that high, we're only losing 18% every single year. So we're not going to end up with a $20,000 car that goes all the way down to only $3.78 for its value. That also doesn't make any sense. Let's say you tried to just plug in one to see what's the value of the car after just 1 year. $3,600. That's a further indicator that this equation is not accurate because that number is really small. You basically lost more than half of the value of the car. We went even below 10,000. We shouldn't be losing more than half of the value because the car is only decreasing by 18% every single year. It's not decreasing by more than 50% every year. So that doesn't make sense. And the reason why that doesn't make sense is because when you're given the growth or decay rate, you should use one of these formulas. So when you're given the pattern as a percentage, you need to use this format to help you write the equation. Specifically, I'm going to use the one with subtraction since I know that the numbers should be decreasing. And in place of R is where I will substitute my decay rate, which in this case is 18% or 0.18. So when I write the formula this way, it will be accurate. The initial value is 20,000. The decay rate is 0.18. If you want to simplify, just subtract the numbers. 0.82. So basically what's happening here, if we're losing 18% every single year, that means we're keeping 82% every single year. And that's where we're actually multiplying by 82. You can think of it that way too, that you're constantly multiplying the numbers by 0.8, sorry, not by 82, by 0.82, because you're consistently keeping 82% of the previous value. So if I think about what the variables in this problem represent, X is my input, so X is years. X is years. Y is my output. It's what this equation helps to calculate. This equation helps to calculate the value. So that's the output. Y is the value. Identifying that will help me finish the last step, which is what will the value be after 5 years. So if you're going to use an equation to solve a problem, you have to know what to plug, which variable to plug a number into. So since X represents years, I'm going to plug 5 into X. And then I can use my calculator on Google. 20,000 times 0.82 to the power of 5. It's about $7,414.80. So that will be the value of the car after 5 years. So the next problem says, hair typically grows about a ½ inch per month. Right now, Matthew's hair is 3 inches long. How long will it take to grow 10 inches? Now, this problem can be tricky because you see a fraction. Because you're seeing a fraction, you might automatically assume that there's a pattern of multiplication, or you might automatically assume that the relationship is exponential. That's not really the case here. What you really have to think about is, how are the numbers changing? Are the numbers changing through multiplication, or are the numbers changing through addition or subtraction? Since the hair is typically growing about a ½ inch per month, that means we're adding on ½ of an inch every single month. That means that the relationship here is linear. there is a pattern of addition. So here we were consistently multiplying by 0.82. Here we're consistently adding by 0.5. So some keywords, if you want to determine whether a scenario is exponential, some key things to look for is if the numbers are changing through a percentage, or if you're told words like double, triple, factor, then if you're told that the numbers are cut in half or the numbers are cut by a third every single time, those are keywords telling us that we're repeatedly applying multiplication to the numbers. So now that I know it's linear, I can use y equals mx plus b to write the equation. The initial value here is 10. That's how much, oh, sorry, it's not 10. It's 3. Right now, that's how long Matthew's hair is. The repeating pattern is 0.5. So in y equals mx plus b, remember the repeating pattern goes in front of x. I'm going to leave it as a positive number because the values should be increasing, growing. They should not be going down. And the initial value stands by itself. It's the number not attached to x. Here, to identify where to substitute 10 inches, again, I should think about what x and y represent. X is my input. That's, in this case, how much time is passing. So what I'm putting into the equation to perform these calculations. Here, my time is expressed in months. So x is the number of months that are passing. Y is my output, what's coming out of the equation. So what the purpose of the equation is for. The purpose of the equation is to determine how long the hair is going to be. That's the output. So y is the length of the hair. Here y was the value of the car. Once I know that, I know where to substitute 10. 10 represents length of the hair. 10 does not represent time. So in this case, I'm not substituting 10 in place of x. I'm substituting 10 in place of y. So now I'm going to solve the equation. Remember, if I want to solve this equation, the first step would be to subtract both sides by 3. This is going to cancel out. The next step would be to divide both sides by 0.5. If you use your calculator, 7 divided by 0.5 is 14. This cancels out. So it will take, remember, x is expressed in months. So this number represents months. It will take 14 months for this to happen.